Low-level systems programming requires more than vibe coding. When applied to deep infrastructure, unstructured generation collapses under its own weight. Asking a generic AI to write code for a novel bare metal environment fails. Because the model trained on millions of lines of standard operating systems, it defaults to legacy structures that don't exist in your kernel. Look at this terminal output. When tasked with writing low-level Rust, the AI defaults to standard library modules, attempts to spawn POSIX threads, and allocates memory on a heap that isn't physically present. In a custom microkernel, these assumptions are fatal. They introduce silent application binary interface drift and trigger unrecoverable hardware traps by attempting to access isolated memory layers. Generic coding assistants prioritize standard web and desktop patterns over physical hardware realities. Custom bare metal architecture requires a tool that abandons legacy abstractions. Nativized vibe coding offers an alternative. This approach strips the model of its conversational freedom and forces it into a highly constrained state. This methodology shifts the AI from a creative coding copilot to a strict, highly bounded compiler engineer. Bounding the AI with absolute, mathematically rigid physical constraints prevents it from inventing its own abstractions. We achieve true efficiency through a zero-token waste deterministic pipeline. Every interaction is strictly routed and executed without burning context on unnecessary data. System stability requires engineering the AI's environment and boundaries first. Only then can the AI safely engineer the code. Consider the architecture of a single address space operating system, or SASOS. In this environment, all processes share one global virtual memory map. Isolation is enforced strictly by hardware memory keys. Every generated line of code risks compromising the physical boundary if it lacks exact context. Feeding a 10,000-line architecture document into a single AI node causes a shotgun approach, spitting out scattered code snippets. As they dissolve, a plummeting token counter highlights the cost. Massive context burns tokens and causes the AI to lose track of hardware constraints. JSON-native sniper agents solve this. These specialized tools use syntax-aware search engines like AST-grep to isolate the problem. Instead of reading an entire file, these tools extract only the specific failing syntax node. They feed the AI the exact structural boundary required. Precision data extraction prevents AI context hallucinations. Controlling the data going into the model ensures the AI stays grounded in deep architecture. Conversational filler, apologies, summaries, and preambles actively destroys context window efficiency in a ring-zero debugging session. We enforce constraint density. This method strips out natural language and forces the AI to reply strictly in unified code diffs or JSON structures. Executing the /caveman command injects a system prompt that overrides the AI's default personality. Conversational text vanishes, replaced entirely by condensed JSON output. This mode restricts the output to raw code patches, exact terminal execution commands, and root cause explanations of 10 words or less. Removing natural language from the debugging loop saves millions of tokens. It keeps the active context window razor sharp. Consistent formatting allows multiple specialized AI agents to pass data back and forth in a shared terminal session without human intervention. Systems engineering requires strict mechanical formatting. Conversational interfaces are a liability in this environment. Type-state prompting enforces hardware honesty upon the model. It locks AI generation within physical hardware parameters. A type-state prompt starts with a physical translation matrix, laying out the exact rules of the custom environment. Standard Rust concepts dissolve on the left, mapping directly to physical microkernel equivalents on the right to prevent using non-existent libraries. The matrix reveals a rigid stop checklist. If the AI attempts an ABI abstraction change, the cursor halts, triggering a red warning. This condition forces the AI to halt execution and explain its reasoning before it changes the application binary interface or adds new abstractions. Requiring confirmation for structural shifts liquidates the risk of the AI creatively bypassing system constraints just to solve an isolated compiler error. A properly constrained AI operates within the architecture. The prompt makes an invalid state impossible to represent. We orchestrate these constraints using a deterministic execution loop, a native wrapper that intercepts the build process. During the interception phase, the wrapper runs the build command, extracts the first fatal compiler error, and drops all background noise. The error signal hits a router. Known errors flow down the green fast path, instantly applying a JSON patch. Unrecognized errors divert to the yellow slow path LLM node. The AI generates a patch, routing this new rule back to the fast path ledger. This permanently compiles the AI's knowledge. The model never spends tokens solving the exact same error twice. The AI functions as a one-time rule generator for a lightning-fast deterministic ledger. It is a tool for knowledge capture, not continuous assistance. Nativized vibe coding permanently strips the AI of its generic, unguided freedom. We force the model to strictly obey the physical laws of a specific, novel architecture. Its vocabulary is limited to valid memory keys and exact atomic operations. This achieves mathematical unrepresentability. The environment is so tightly bound by type-state proofs that an invalid state simply cannot compile. Look at this compilation log. Hardware capability violations and cross-domain memory leaks fail the type-state checks. They are caught by the compiler before reaching the physical executable phase. Sniper tools and token compression transform the AI into a mathematically bound execution engine. Architectural precision drives token efficiency, surpassing the utility of expanded context windows. Deterministic loops ensure system stability by strictly bounding and directing the large language model. Absolute structural control eliminates conversational drift. As this mechanical lock snaps into place, it demonstrates the precision required for high-stakes generation. We must view the AI as a bounded component operating inside a rigid state machine, rather than a human-like collaborator. To get an AI to build a perfect system, you must first architect a perfect deterministic system for the AI to live inside.